to talk about half-life. So, start with a definition. Half-life is the time that it takes for a radioisotope, for half the amount of radioisotope to decay. So what that means is, let's say you had 100 grams, or in this case here, this picture, we have 100 kilograms of a particular isotope. All right, everyone see how we're starting here with 100 grams? So when something is radioactive, when something is unstable, we know it's going to undergo decay. Whether that decay is alpha, whether it's beta, right? It depends on which particular isotope it is. But it will break down. And you know that when it breaks down, it becomes something else. So if we had a certain amount, in this case we were starting with 100 kilograms, if we follow this from 100 kilograms down to 50 kilograms, 50 kilograms is when you now have half of what you did. Right? We now have half the amount that we started with. So the amount of time that it takes for that to happen is defined as the half-life. Right? It's the amount of time. So in this case, the half-life is about 12 years. Now, the half-life should be constant. Meaning, if it took 12 years to change from 100 to 50, then half of 50 is 25. So the amount of time it takes to go from 50 to 25 should be the same amount. It should be 12 years. So if we follow down here on the graph, from 50 down to 25, we went from 12 to 24. Or in other words, 12 years. So the value of half-life, the amount of time, remains constant. The amount that you have just will always be cut in half. So if we were to continue on with this, if we right now have 25 grams, right, half of 25 grams would be 12 and a half. So it would take another half-life to get to 12 and a half grams, which would be somewhere around here. And this can keep happening in perpetuity. You can keep cutting something in half. It's going to take 12 years. Cut it in half. It's going to take 12 years. Cut it in half. It's going to take 12 years. Right? Now, whenever there is radiation around, like you've heard of like nuclear fallout, you've seen movies with nuclear war, post-apocalyptic wars, and everybody's worried about the nuclear fallout. And, you know, the radiation that's released into the environment when there is like a nuclear explosion, it's going to, depending on which isotopes are present, it could take thousands of years for the radiation levels to go down to the point where it's safe. Right? Like in Chernobyl. In Chernobyl, the amount of radiation that was released, they built a giant concrete sarcophagus, like tomb, over Chernobyl to help prevent the radiation from leaking out. And even still, you can't just like go up there. Like that whole town is gated off. You can't go near it. They do allow scientists to go in real quick and take readings and come back out. And I think they might actually allow tours now to see like the messed up power station. It's kind of morbid, but they do limit you. Like you can only be on the grounds for maybe like 40 minutes or something like that. I don't know that I would do it, but I know that they do allow it now. Okay, so does that definition make sense? The half-life. Every substance that's radioactive has a different half-life. Half-lives range, okay? They can be seconds all the way through millions of years. So I might have a radioisotope where the half-life is 2 minutes. Or there might be a radioisotope where the half-life is 500,000 years. Okay, in other words, anything with a half-life that long is going to far outlive you, right? All right, so if we understand the concept, let's try some calculations. So I've got an isotope of strontium-90 here, and the half-life is 28.8 years. Just for simplicity, let's just round this to 30, just so to make this quick and easy. Okay. So if the half-life is 30 years, and let's say we start with 10 grams of it. Well, if we start with 10 grams, because we rounded the half-life to 30 years, it's going to take about 30 years for there to be 5 grams remaining of my isotope. And then, after a total of 60 years, which is 30 additional years, it'd be about 2.5. So the question is, how much are we going to have left after a total of 150 years? Well, if 150 years passed and we've said the half-life is 30 years, then essentially 5 half-life periods will go by. Do you guys see that? Okay, so time divided by the half-life period. This is going to be 150 over 30 means we're going to have 5 half-lives. N is the number of half-lives. Okay, so that means I'm cutting this in half 5 times. So 1.25 after another 30. This is going to be 0.625 after another 30. And then after another 30, maybe 0.3125. And that's a total of 150. So the answer is we're going to have about 0.3125 after 150 years. Now we did round that, so this is not exact. But this is just for the purposes of demonstration, understanding the concept of how many half-lives have passed. Okay. While that gives us a picture of the types of numbers to expect, there's an actual formula that we can use. And so the formula is A sub t, where A sub t is the amount after time has passed, A sub naught, this little 0 guy here, you guys see that 0 subscript? All right, that's called naught. That means initial or beginning. So the amount at the beginning. And I already addressed what n was. Oops. N is the number of half-lives. And the number of half-lives can be found by taking the time divided by the half-life length. Then the last example, the time was 150 years. The half-life length was 30. So we did 150 over 30 to give us 5. Okay? So let's try the example. How much of a 3-gram substance is left after 300 minutes? And they are telling us the half-life is 15 seconds. Okay, so when they say how much is left, what they're asking for is this. A sub t is how much is left. So let's plug in what we know. So A sub naught is the original amount, and the original amount is 3 grams. 3 grams is now multiplied by 1/2, and that 1/2 is raised to the n power. But the n power is really the time over the half-life. Right? So 300 minutes is the time. 15 seconds is the half-life. But here's the problem. Or actually, can you tell me what the problem is? Can I solve for n yet? What's the problem? Units. They are in different units. It doesn't matter which unit you choose as long as the units cancel, which means they have to be the same. I'm just going to turn minutes into seconds. So 300 minutes times 60 seconds per minute. This is 18,000 seconds. Which is a long time relative to the half-life, but that's what's there. So, okay. When you plug this into your calculator, it's important that you have parentheses where they should be so that your order of operations are correct. All right, so plugging this into the calculator, I would type in 3.00 times 1 divided by 2, and then raise it. Make sure that when you raise it to the power, whatever is in the power is in parentheses. And I'm getting 0. Okay, you know what? Let's rewind this back a second. I think I had a typo in here. I think what I meant to type was seconds, not minutes. So let's just change this so that it's a workable problem. Because that kind of didn't make sense. All right, so our half-life is going to be 300 seconds over 15. Okay, that is much more reasonable. So the amount that we're going to have is 2 points, we'll call it 2.9. Sig figs are a little bit of a mess here. 2.9 times 10 to the negative 10th grams. Did you guys get that? Okay. And if you think, that's a really, really tiny amount, just stop and think about it. You took a number and you cut it in half. I mean, a lot of times. 300 over 15. 20 times. You cut it in half 20 times. It's going to end up being a small number. Okay? All right. Before I talk about the next equation, I just want to talk about a little bit of algebra here. So this equation right here, you remember when I said to you that however many variables there are, that's how many versions of an equation there are? Okay, so let me just rewrite this a little bit. A sub t is equal to a sub naught times 1/2 raised to the time over half-life. How many variables do you see in that equation? 4. There are 4. Which means there are 4 ways for this equation to eventually be rearranged. Now, the first one, well, this is the first one. The second one involves just rearrangement with a little bit of algebra. And so what variable would I be solving for by simply dividing? What is the only other variable I could solve for if all I do is divide? This guy, right? So I could solve for a sub naught by simply dividing out all of this. So what that would look like then is a sub t over 1/2 raised to the time over half-life. That would be equal to a sub naught. This is the second equation. I just moved everything over to the other side. You guys okay with that? Now, because it's in the denominator, you got to be a little extra careful because now you have a parentheses with an exponent that has parentheses that is in your denominator. So order of operations is crucial to getting these right. So double check the way that you are figuring this out when you're using your calculator. All right, so just put a box around the, that's not a highlighter. Let's put a box around these. Okay. All right. So the thing about the half-life equation is that in order to solve for the last two variables, the time and the half-life, involves what we call logarithms. Now, we're not all necessarily in the same place and have the same background experience with logarithms, but this is not a math class, so I'm not going to teach the fundamentals of logarithm. I'm just going to show you how to work around it so that you can do enough in this class to do the chemistry behind it. Okay, so basically, this might make more sense if I'm going to do these from scratch. Okay, so right now, don't write anything down. Just watch. I'm going to be doing it right. Just watch what I do, okay? So here's our first equation. Okay? My goal right now is I want to find time and I want to find half-life. I want to solve for those two variables. But the problem is they are in the exponent. And one of the purposes of logarithm is to find and isolate the exponential values. Okay? So what I'm going to do first is I'm going to divide a naught out of both sides. And this is what's going to result. Can you guys see what I did there? I just divided both sides by a naught. It canceled on the right side, and now it's on the bottom of the left side. All right. So when you use logarithms, it's just you apply logarithms. It's just like any equation. You have to do the same thing to both sides, right? So when you apply logarithms, in this case, we're using what's called natural log. There's different kinds of logs. It doesn't really matter which one we use, the natural log or base 10 log, is because they're both going to end up canceling out. I'm just going to use natural log because in science, usually we use natural logs. So if I apply what's called a natural log to both sides, it's going to take that value on the left and just putting it inside a parentheses, like it's a function of, okay? And when I do the natural log of the left side, it brings this guy, it brings this down and becomes a coefficient. And so what we have then is time over half-life multiplied by the natural log of 1/2. Okay, this step here is applying the log. And again, this is not, I don't need you to know this necessarily. I'm just trying to show you how I'm going to get to the equation I'm going to get to. All right. So think of it as this is one variable, this is one variable, and this is one variable, okay? So think of it as right now you're looking at three variables. How could I rearrange this, or what could I do to solve for t over HL? How do I solve for just this? Yeah, divide, right. So the next step would be ln of a sub t over a naught is divided by ln over 1/2, and that is set equal to time over half-life. Okay. This equation right here, this equation will be given to you. So will this equation. All right? When I give you this equation, can you guys go from here to here on your own? because you're just dividing by one thing, okay? If I give you this equation, the goal is to be able to solve for either this or this. So the easier one to solve for is time. How could I solve for just time? How could I get time all alone? Good. Multiply by just the half-life. Okay, so we have a divergence here. So when I multiply both by half-life, this is what I get. This is what we call equation 3. It is rearranged to solve for time. Okay, but there are times where you'll need to solve for half-life. And in order to solve for half-life, do you guys remember how with density, if I said, how do we solve for volume? You would say, oh, multiply both sides by v and divide both sides by d, and then you would get this. You guys remember that? How effectively these two things traded places? Well, the same thing's going to happen here. So if I said, take this equation, think of this as just one thing. And we have time over half-life is equal to this thing. So if I want to solve for half-life, multiply both sides by half-life, divide both sides by this. And then we're going to get half-life is equal to the time divided by all of this. That's equation 4. So, logarithms are applied to the original equation. We then get a derived equation which brings the time and the half-life down out of the exponent. Once it's out of the exponent, you're just moving stuff around like it's regular algebra. The logs is only used to bring it down from the exponent. Okay, so you don't need, I'm not going to ask you to do that, the log step necessarily, because we are going to give you the equation, but you have to practice this equation well enough to be able to get to there and to get to here. That's your job, all right? Because we need to be able to solve for all 4 variables. Okay, so let's try a couple of problems. I'm going to add another page here. Just find some place where you can write. If you're out of space on your note packet, then just do this anywhere else. And we'll do like one of each kind, okay? So here we have a radioisotope. It's got a half-life of, we'll say 20 days. Start with 75 grams. How much is left after (90 days)? Okay, so think of the 4 equations that we had. Think which one you're going to use. Which one is set up to solve for what I'm asking for? I'm asking for how much is left. Which one of those equations suits that question? The original, which is the first one. The second one, which is solve for A naught. Or the third and fourth, which involve logs. It's not the last 2. It's one of the first 2. The first one. It's the first one. So trying to find the new amount. A sub t is the new amount. Okay, so plug them in, see what you get. How much is left? Maddie, what'd you get?
3.315 grams.
Yeah, we'll go 3.31. Okay, these numbers I gave you, the sig figs are kind of sloppy, right? In general, you try to follow the rules. Consider everything you're doing here multiplication and division, right? So in essence, what that means is you're looking for the fewest number of sig figs present in the problem. You're not adding or subtracting anything. Okay, so it's not like it's complicating it. It's just whichever one is fewest. And I didn't give you enough sig figs, but I could pretend I did by saying 90.0, 20.0. Hey, look, we have 3 sig figs. Okay, all right. Let's try another one. Let's do one of the second variety. So, the half-life of an isotope is 15 years. Oh, get my sig figs right. 15.0 years. And 225 years have passed. If let's say we found, or we have now, we currently have 0.00175 grams of a radioisotope. What was the original amount? So I'm giving you the half-life, I'm giving you the time, and I'm giving you the current amount. What was the original amount? Well, consider your equation again. Which equation are we going to be using? The second one. So, second equation is a sub t over 1/2 raised to the time, or half-life, is equal to a sub naught. So, fire away, see what you get. We'll go with 3 sig figs here. Who's got this one? What was the original amount? Jason?
Is it 57.3?
Yeah. How are we doing, guys? So far, so good? Okay. All right. As you can imagine, the third and fourth examples are going to be a little bit more work, but not too much. Not too much. Okay. So let's say we start with 75 grams of an isotope, and we end with 0.00412 grams. So we have a starting amount, we have a final amount. Half-life of this isotope is 2.5 days. How much time has passed? Okay, so they're asking for the time that has passed. We know we have already rearranged and solved for that up here. so amount, let's go ahead and label this just to make sure we know what we're doing. This is A sub naught, this is A sub t, and that's half-life. Okay, so for those of you who don't know, there is a natural log button on your calculator. It is on the left-hand side. When you hit the natural log, it automatically initiates a parentheses for you. Okay, so you would literally just type ln and 0.00412 divide by 75.0 and close that parentheses, and then divide by ln 1/2, close the parentheses. I guess we're stuck with 2 sig figs here. How many days have passed? 35. Or not year days, sorry, years. Your unit is years. Wait a minute. Days. No, I was right, days. Days. You guys still doing good? Okay. Let's try one of the 4th variety. Okay, so what have we not solved for yet? We have not solved for half-life yet. Okay. So for this isotope, let's say that originally, let's say that we start with, we'll use percentages because percentages are used a lot. We start with 100% of a sample, and we end up with 0.621%. Okay, and the time that it took for this to happen, let's say 444 days. What's the half-life? And we'll put a decimal point in here to bring that up to 3 sig figs. What's our half-life, guys? Actually, let me double check that. Yeah, okay. I would suggest, I didn't mention this before, I would suggest putting parentheses, a double set of parentheses, because we effectively have two variables in a denominator, so then your number is going to differ if you don't. So you're going to need these parentheses in order to do this right, these ones right here. Okay, what do we get? Yeah, 60.6. What did I say? Days? Yeah. Okay, those are how you carry out half-life calculations. Just understand the general ideas, right? The amount that you have of something that is radioactive will only go down. It's constantly breaking down and turning into other things. So as time goes on, you have less and less and less and less of the original isotope that you were focusing on. Now, the matter that it turns into doesn't disappear, it just turns into something else. Okay? As far as what to calculate, what you need to know how to do it, you, again, will be given, how do I make this stand out? You'll be given equation 1. I'm going to expect that you can derive equation 2 on your own. You will be given equation 3. And you need to get to these two variations on your own. It involves a little bit of algebra. Okay, so those two equations are the ones that you are going to be given. You're going to be given 1 and 3.
Are these notes on Schoology, like yours?
What, the ones I just did?
Yeah.
No, but this video is being recorded.
Okay.
And I'm just going to post it as soon as I'm done because I know I have people missing next class. Okay, so the best way to get good at this is just do a bunch of practice. So homework 3 are your half-life problems, and that is your homework. Question, Alex?
Are we going to be graded on changing problem 3 to like the different subset?
Yes. Yes. You have to be able to go from here to either this form or this form, depending on what is needed in the problem.
So we can't just memorize the equation?
I mean, I guess you could memorize it, and if you memorize it correctly, then you won't have any problems. Is that easier to memorize it? I think it's easier just to move stuff around. Because I will give you this problem. But so here's what I recommend. Learn how to do it, and you might end up memorizing it in the process. Okay? But try to learn it first, because if you learn it and if you forgot the details, maybe you'll probably be able to figure it out when you need to. Okay?